Hey, College Math, welcome back. Here is the second part of 1.5. This will be our last video for chapter 1 before we move on to new stuff, right? We're going to end by covering graphs of numerical variables, okay? In 1.5.1, we talked about graphs for categorical variables, bar graphs and pie charts. Here we're going to look at two other graphs, okay? And so our objectives are to read, draw, and correctly label histograms, and then to read line graphs. We're not going to be super concerned with making line graphs, more so with histograms, okay? So when we think about numerical and quantitative variables, we're going to want to resort to histograms or line graphs, okay? And so we'll start with histograms. These are they look pretty similar to bar graphs, but there's a few couple differences, and we'll go ahead and write them down here. For histograms, our bars do touch, okay? So remember in the bar graph, we wanted to keep those bars separated. Here with a histogram, since a lot of the times, most often we represent continuous variables, and when we think of the number line, we think of it as like a continuous thing. There's no separation. And so that's why the bars do touch. They're kind of a continuation of each other. The categories on the horizontal axis. Okay, so if you remember from a bar graph, we had categories like, if it was different colors, they'd be red, blue, green, etc., right? So categories on the horizontal axis. Sorry, that's a Z, I promise. On the horizontal axis are number ranges. Okay, number ranges, and we'll look at that here in a little bit. And these categories, we're actually going to call them, so they're called bins. Okay, and so when we talk about a bin is going to be the categories on our horizontal axis. Okay, and so then speaking of bins, with that, we have what's called the bin width, which just tells you how big the range of numbers is for that category. They're all going to be the same width, and so that's why we got to make sure we figure it out. We can get that by taking the maximum, so the biggest data value, minus the smallest data value, the minimum, and then divide it by the number of bins that we want. Okay, so if I want 5 bins, I would divide by 5. If I want 10, I would divide by 10, etc. Right? And so when it comes to bins, all right, so a little note here, either you choose number of bins. Okay, so sometimes the problem won't tell you, so you just kind of choose the number of bins that you think would make it look pretty decent, make the data set look decent. Usually you want to choose at least 5. Definitely never want to go less than 5, because then we don't get a good shape on our histogram. Or the problem tells you, okay? And sometimes the problem even tells you what bins, like the specific bins that they want, and you don't even have to find those ranges. Sometimes they're just given to you, okay? But either you choose the number of bins if they don't give it to you, or the problem will tell you either how many bins or what bins exactly to use, okay? Let's go ahead and take a look at what that might look like here in this first example. Below is a data set of weights in pounds of lotads captured on Route 102. These are the lotads, these cute little guys, okay? And so I kind of collected some data on weights, how much they weigh. Here we have a total of 30 data points, right? So sometimes it's always good to just write down how many data points you have. So we have 5 by 6, so we have a total of 30. Okay, we're going to want to create a frequency distribution of the above data using 5 bins, okay? So just like with a bar graph, the first thing we do before making the histogram, in order to make the histogram, we need to make a frequency distribution, okay? And before we can make that, we have to determine the bins, because on the left side of our frequency distribution, instead of the category, we're going to have those number ranges, those bins, okay? Let's go ahead and start by finding our bin width, okay? So bin width equals the maximum, so our biggest data value. They nicely organized it for us from least to greatest, so it's going to be 6.8 minus 4.0 is our minimum. That's our smallest data value. And we'll divide by 5, because that's how many bins we want, okay? And so we're going to get 0.56 from doing this. And we always want to round up, okay? And we want to match, so the decimal amount on this bin width, let's match it with the data values. Okay, so here we have all in the tenths place. So I want this to be in the tenths. And no matter what I have here, even if this was like 5, 4, I'm gonna actually just always round that up to the nearest, in this case, 10th. So I'm gonna go to 0.6, okay? And the reason why is because if you round it down, you're no longer gonna have enough space to get all of your data values, okay? And so maybe write yourself like a little note here, like always round up, okay? You could technically, if you wanted to, take this all the way up to 1. It wouldn't be such an issue, but that will change the shape of your distribution. So always just try to match the amount of decimals in the data set. Okay, so I have tenths here, so I want to match this to be tenths. Okay, and then always round up to fit all the data. Okay, and so now that I have my bin width, I can make my frequency distribution. Okay, and so I'm going to make a table like we have in the past. One side is going to be the bins. And here I have 5. So I'm going to want enough space for 5. Okay, so my bins are over here. And here's how I'm going to write the bins down. Okay, the notation is going to look a little funky, but just kind of stay with me here. I'm going to start with my smallest number. So 4.0 is where my starting point is, 4.0. And then here is like the notation that we use for our bins. So 4.0 is less than or equal to x, which is less than or equal to, or sorry, just less than 4.6. Okay, so let's kind of rewind back and see where I got some of the stuff, right? So 4.0 is my starting value. This notation right here, this less than or equal to x is less than, is telling me that I want all the numbers between 4.0 and whatever next number I have. I get this next number by taking 4.0 and adding my bin width. Okay, so 4.0 plus 0.6 is 4.6. Okay, and the fact that I have only less than here, it's not a mistake. This is intentional. That means I don't want to include 4.6 in this category because I'm going to include it in the next category. That's my starting point, my starting value for the next bin. 4.6 is going to start off the next one. Less than or equal to x, less than, and then I add 0.6 again. So that's going to give me 5.2. Okay, I repeat that process. So start with 5.2 here, less than or equal to x, less than, I add 0.6 to get 5.8. Start with that one in the next one. 5.8 is less than or equal to x, is less than 6.4. Okay, and now I need one more bin. And so start with 6.4, less than or equal to x, which is less than or equal to, in this case, since it's going to be the last one, 7.0. Okay, and so it's okay if this one is a little bit bigger than your biggest value. You just don't want this to be smaller than your biggest value, right? Okay, because then you won't be able to include that biggest value. It's okay if this is bigger, because then I will be able to include 6.8 in that one. But if it was smaller, then I would leave 6.8 out. Okay, and so these are my bins. All right, I have 5 bins. You always want to make sure it matches the number of bins that you chose or that you were told to use. And now that I have that, we just got to include our frequency. Okay, and what is our frequency here? It's the amount of data points that fall in this number range. Okay, so go up here, start with the first bin. I want all numbers that are between 4.0 and less than 4.6. I don't want to include any 4.6s in this column if I have 4.6. Okay, so I count 1, 2, 3, 4, 5. And I stop there because I'm not going to include 4.6. So I have 5. All right. Starting with the next bin, I can include my 4.6s here, but I'm not going to include any 5.2s. So 1, 2, 3, 4, 5. And that's it. Okay, go ahead and repeat that process just to save us some time. I'm going to do the rest for you. 9, 9, 2. Okay, but maybe pause the video and go back and check to make sure that you understand why that one's 9, why that one's 9, and why that one's 2. Okay, and it's always nice to just go through and add this all up and make sure it matches up with your sample size, right? So 5 plus 5 is 10, 9 plus 9 is 18, 28 plus 2 is 30. Okay, so we're good. Now we're going to go ahead and make our histogram using that frequency distribution. Okay, and so it's the same idea. I'm going to have a vertical axis, and I'm going to have a horizontal, there we go. I'm going to have a horizontal axis as well. Okay, and then my title, I can just say weights of LOTADs captured on route 102. Okay, so there's my title. And then I'm going to go ahead and let's see, looking at my vertical axis, that's going to be my frequency. My biggest value is 9. So it looks like I want to scale this by 2s. 2, 4, 6, 8, 10. And then I don't really need to go all the way up there, so I can just end it there. Okay. And so this is my frequency. So here I would say this is the number of LOTADs. Okay, the number of LOTADs that have that weight range that we'll have down here. Okay, so here we're going to put our axis label for the horizontal axis is the weight. Okay, and that's in pounds. Okay, and now I'm going to want to mark off my my bins. Okay, I have 5. So here's 1, 2, 3, 4, and then I can stretch this out a little bit. 5. Okay, and the way you label these parts right here, it changes a lot. The way that I like to do it, and I think this way makes more sense, is just put that bin label right here for each of these little sections. So here I'm going to label this with 4.0 less than or equal to x is less than 4.6, and then 4.6 less than or equal to x less than 5.2, 5.2 less than or equal to x is just less than 5.8, and then 5.8 less than or equal to x, which is less than 6.4, and then 6.4 less than or equal to x, which is less than or equal to 7.0. Okay, that's the easiest way to do it. One thing I forgot to mention up here, another name for the frequency distribution is a class count table. Okay, you're gonna see that more often, in my opinion, than frequency distribution. I just wanted to tie it back to how we did frequency distribution in 1.5.1, where bins, another way to think about a bin is a class, and then another way to think about the frequency is the count. Okay, so that's another way to think about frequency distribution. Now we just draw our bars. That's the easiest part, right? Label the axis, scale, 8, 10, and then I just draw my bars. So this first one is 5. This next one is also 5, and notice how the bars will be touching each other. They're right next to each other as opposed to spaced out. And then I go all the way up to 9 for my next one. And then 9 as well for the next category, the next bin. And then the last bin is just a size 2. Okay, and so there's our histogram. All right, we have a title, we have all of our axes labeled, we have the labeled and scaled, and then the categories are labeled as well, the bins. And then we have our bars. And then same thing as last time, we can fill these bars in if we wanted to. It's definitely not required though. Okay. So all things to keep in mind for in case I give you draw me a histogram on the checkpoint. Okay. You're going to want to make sure the title is included. You labeled the axes with the scaling, the categories, and the extra label here, right? That's just as important. Okay, we got line graphs. All we really want to worry about with line graphs is to make sure that we know how to read them and when they're used, okay? Typically, we use line graphs to track change over time, all right? And so what that means is that the horizontal axis is usually is a measurement of time. Okay, and so that's really the main idea of line graphs. We can use it for other purposes, but typically we track it, or we use it to track how things change over time. Okay, so let's go ahead and do this last example where we're just kind of reading through a graph, right? So answer the questions below about the provided multi-line graph. Okay, a multi-line graph is when I have multiple lines, right? One represents one kind of quantity, while the other represents a different quantity, right? So we have the cost of 21st century natural disasters, and it describes to us here the cost of natural disaster losses worldwide from 2000 to 2021 in billion US dollars. Okay, and that's good that they gave that to us right there, because if you notice, this left, the vertical axis is not labeled, but because they gave us this right here, the fact that this is measuring the cost of natural disaster, that's good enough, right? And one thing they could have also given us here is the fact that these are years, but again, if you look at these numbers, people would have guessed that these are years, okay? And so also because it's a line graph, right, we would have guessed that it's a time measurement. And so in those cases, that's okay to leave out the units. It's better to put the units there, less work for the reader, right? Especially in other cases where it's not so obvious, where we're not working with a line graph, right? All right, so A, in what year, or in about 1 year, was there the most economic losses and how much money was lost? So we're looking at the most economic losses. So that's going to be our orange category. So I'm looking for the peak. Okay, so it looks like it's about here. And we're going to maybe say that that's somewhere in about maybe 2011, it looks like, right? Because it's a little bit past the 2010 mark, right? And as far as how much it was, well, it looks like every other line is 200,000, which means that every line is 100, or sorry, 200 billion, right? Because it's in billions of US dollars. So every line is 100 billion. So right here is 500 billion. And this is about halfway there. So we're going to venture and say it's about $550 billion, okay? 550 billion. We'll give it an extra L. Billion was lost in economic losses. Okay. Next question, was there an instance where the economic losses and insured losses were the same? If so, in what year? So by same, we mean, you know, they had the same amount of loss. So pretty much what we're looking for in terms of graph is, do they intersect? Okay, maybe it looks like they're projecting it'll intersect in 2021, but it doesn't intersect at all on this graph. Okay, notice how there's no intersection point. So we would say no, because there is no intersection point between the two lines. Okay, and that's what we're looking for. And then the last question, how much more expensive were economic losses than insured losses in 2005? So how much more expensive? It looks like we're finding the difference between the two, right? Okay, how much more expensive? So I'm going to want to find the amount of economic losses and the amount of insured losses in 2005 and just subtract them. Okay, so 2005 is here. And so I have, this is my insured loss and this is my economic loss. And we can always just approximate, right? So here for my insured loss, that looks like it's about 140 billion. And then for my economic loss, it looks like it's about 350 billion. Okay, so we'll just have to subtract those. So 350 billion minus 140 billion, right? Is that what I said up there? Yes. That comes out to $210 billion more. Okay, so hopefully that helps in terms of reading the line graphs, right? And it's always okay, like in this case, we did a lot of just estimating, right? we're not looking for, like, I was not expecting you to know the exact amount of economic loss in 2005 from natural disasters, right? Just kind of give it a guesstimation. That way you can give kind of a rough estimate and maybe understand some of the changes a little bit that go on from the beginning to the end, okay? And if I ever give you a graph like this, or just any other graph where it's not super clear, be okay with trying to give it your best estimation, okay? All right, hopefully that sounds good, y'all. We did histograms and line graphs for numerical variables, okay? And we'll go ahead and end chapter 1 with that, okay? I'll see you in the next one. Enjoy the rest of your day.